Okay, so we left off here at section 24.7, which deals with disaccharides. And just reading off the slides, it says that disaccharides consist of two sugars connected through a glycosidic linkage. And the glycosidic linkage is really the most important part. It's the part that governs the identity of, or helps to identify, the type of disaccharide. Okay, so it says here that the glycosidic oxygen connects carbon 1 to carbon 4, and so we call this a 1,4 disaccharide, like in maltose. Okay, maltose is made from 2 units of glucose. This is a glucose molecule here. This is a glucose molecule here. Now, the linkage is what governs whether this is maltose or not, okay? Because you can have 2 glucose molecules linked together to make a disaccharide that's not maltose, and I'll explain that later on. But the linkage is alpha 1,4 because the bond that's going to the oxygen off of carbon 1 is pointing down. So that's alpha 1,4, right? The configuration at 4 doesn't change. It's always going down in equatorial. But again, at the anomeric carbon, because this is a glycoside now, right? This carbon, let me highlight it in yellow. This is a glycosidic carbon, isn't it? Because it's got an ether here and it has another ether here on it. Okay, so that's a glycoside. So again, the glycosidic carbon, the bond going down here is alpha, so we call that an alpha 1,4 linkage. Now this is a hemiacetal here, right? This carbon is a hemiacetal. And so maltose is a disaccharide that's a reducing sugar, because when we have a hemiacetal, it can exist in an open chain form where we have the aldehyde that can be oxidized and in turn cause the reduction of, let's say, copper 2 or silver, for example. Okay, so since the hydroxyl on the hemiacetal is pointing down, you would actually call this alpha maltose, is what you would call this. And if it was pointing up going this way, that would be beta maltose. Because again, this part of the maltose is never going to change. The linkage, this bond is always going to be pointing down. Okay, so that covers maltose, and I explained why maltose is a reducing sugar. If you have cellobiose, cellobiose is made from a glucose and another glucose as well. What's the difference? It's the way the glycoside is linked, right? This is my glycosidic carbon, right? I have an ether here and I have another ether here. So that is glycosidic. But the bond that's going off of carbon 1 is pointing up. And so it's a beta 1,4 linkage. Okay, and when I have a beta 1,4 linkage, I have cellobiose. It doesn't matter. It doesn't matter whether the carbon on the hemiacetal, it doesn't matter if this carbon is pointing up or down. The fact that it's pointing up, this would be beta cellobiose, okay? But it could be pointing down, and it would be alpha cellobiose. But the idea is that the linkage is what determines whether it's cellobiose or whether it's maltose. So again, cellobiose and maltose, okay? And this is a typo here. This should say cellobiose. So cellobiose and maltose only differ at the stereochemistry at the anomeric carbons. That's it. Okay, that's it. There we go. In fact, I don't like the way that that's written, actually. It shouldn't say stereochemistry at the anomeric carbons. It should say the linkages, really. So we'll put here, they differ at the glycosidic linkages. So glycosidic linkage. I'd say that's more accurate. Okay. All right. Let's move on from there. Another disaccharide that you should know is lactose. You don't have to be able to regurgitate the structure of lactose necessarily, but you should know that lactose is a disaccharide made from galactose and glucose. Now look at the linkage here. The linkage is beta 1,4. Okay, it's a beta 1,4 linkage. The fact that this hydroxyl on the hemiacetal is pointing up, it's neither here nor there. Okay, since it's pointing up, this would be beta lactose, but it could be pointing down and it would be called alpha lactose. And lactose is also a reducing sugar because it has a hemiacetal. So that's lactose. Now the last disaccharide that we look at is sucrose. And sucrose is table sugar, right? You go to the grocery store, you buy a bag of sugar, what you're buying is sucrose. And sucrose is a disaccharide that's made from glucose and fructose. But if you look at fructose, there is no hemiacetal in sucrose, and so sucrose is not a reducing sugar. So what have we learned? Cellobiose, maltose, lactose, those are all disaccharides that are reducing sugars. However, sucrose is not a reducing sugar. That's something that you need to know. All right. The fact that honeybees can convert sucrose into fructose, glucose, and sucrose as well, I guess that's important, but that's neither here nor there really to me. Now, let's take a look at some disaccharides. We did not even concerned with the name of the disaccharides. Well, the last one is sucrose, it tells you. But we just want to know, are these reducing sugars, yes or no? Could anybody tell me, would A be a reducing sugar, do you think? Would A be a reducing sugar? Does it have a hemiacetal? Absolutely, Jisoo. Yes, 100%, right? This carbon has a hydroxyl and an ether on it, so the answer is yes. Okay? If we look at B, the answer is no, because here we have a glycoside, right? This is an acetal here, and then we have another acetal here. And so the answer is, since this carbon is, this is a glycoside, so therefore the answer is no. And you could say there's no hemiacetal. And then in sucrose, we just learned on the last slide or a couple of slides ago that not a reducing sugar. Why? Because there's no hemiacetal. That's it, my friend. All right, and that's everything about disaccharides. Let's talk about polysaccharides. It's just some kind of FYI information. And when I say FYI, it's FYI information that you need to know. Cellulose is the most abundant organic compound on the earth, and it's a polysaccharide that has, says here, between 7,000 all the way up to 12,000 glucose units that are connected through what? Beta glycosidic bonds. That means that this particular bond right here is going up, right? It is beta, okay? Because it's pointing up. So here, all those bonds are beta 1,4 linkages, okay? So we call this a beta 1,4 linkage. So there you go. So that's cellulose. And the reason that cellulose is so strong, when you find cellulose where, I mean, it's found in things like wood and plants, you know, it gives stalks on a plant, its strength. It's because, and you can't really tell by this structure that's on here, but it's because it can form these like long strands with lots of hydrogen bonding, and that's what gives it its strength. Anyhow, cellulose can be spun into fibers like rayon. It can be made into wraps like cellophane, or, you know, there's cellulose in the paper that you use to write your notes on, for example. Starch, on the other hand, is glucose, just linked together, but the difference is it's an alpha 1,4 linkage. Look, here you have all the linkages. It's just glucose, but the difference is that these are pointing down, okay? These are down, and therefore they are alpha. So we say it's alpha 1,4 linked. Now, starch is actually made of two things. Starch is made of amylose. You see the structure here, and amylopectin. Most of starch is actually amylopectin. About 4/5 of it is amylopectin. And the difference between amylose and amylopectin is that amylopectin has branches off of the main chain. So we call this a 1,6 branch because it goes off of carbon 6 and attached to carbon 1 like this. And it has these branches about every 25 glucose units. So approximately every 25 units, you get a branch. And the difference between amylopectin and glycogen is that glycogen is the energy reserve for animals, and it's more highly branched. So I'll just write it down here. Glycogen and glycogen. It's the same structure as amylopectin, except why don't we write this up here? So branch. So in amylopectin, we'll put branches every about 25 units. And the only difference is that glycogen has branches every about 8 to 12 units. And there you go. Yeah, and there we go. So we'll say 25. I put in my notes 25 to 30 units. I don't remember exactly what it says in our textbook, but there you go. And we're going to skip section 24.9, and we'll also skip section 24.10. So what are the things that we covered in this class or in this lecture? On carbohydrates, we talked about Pyrenees rings. I expect you to be able to draw the Haworth projection or the chair of a Pyrenees given the open chain form. You do not have to do it for a Pyrenees ring. Then we talked about all these different reactions. We talked about acetylation first, and we talked about how acetylation can take something like a polyhydroxy aldehyde or ketone, again, a carbohydrate, how it makes it more easily purified because you don't have all those polar hydroxyl groups. We talked about alkylation, and it has the same kind of effect. We take an alkyl iodide or like methyl iodide and then a base like silver oxide. Then we talked about glycoside formation using an alcohol and acid. We talked about reduction to make it alditol. So this is an alditol that's shown here. So we have our, where is it? Alditol. Then we talked about oxidation using bromine and water at a pH of around 6 to make an aldonic acid. So we have our aldonic acid. And then you can use stronger oxidation conditions to make an alderic acid. What else did we talk about? Is there more? Yeah, we talked about chain lengthening. So this is the Killiani-Fischer synthesis. All right. And on the bottom, we talked about the vol degradation. So vol degradation. And that is all the new chemistry that we learned in this chapter.